Okay, guys, we are going to go ahead and start our unit on solutions. You're going to go ahead and click on the notes or take out your own notes and follow along depending on what period you're in. You'll be just taking notes if you're in for one period today, and you will be doing a worksheet the second period for the kids that have two periods. So go ahead and open up the notes, follow along, or just follow along with what I do, and pause and take notes as we go. This will most likely be in 2 increments, 2 20-minute note sessions. You should be watching both of the note sessions if it isn't 2. Okay. So we are starting a unit on solutions. We just finished up, obviously, with stoichiometry and carrying on with converting things into moles. We're going to talk about different types of solutions first. So what are the 2 types of mixtures? So when we're dealing with mixtures, let me get my correct color pen here. When we're dealing with mixtures, there are 2 types of mixtures we know about. We learned about this before. There's homogeneous mixtures and heterogeneous mixtures. No, wrong color. Homogeneous. Remember, homogeneous mixtures are the same throughout. You can't tell a difference whenever you see homogeneous mixtures, and then heterogeneous mixtures are different throughout. Okay, so some examples. Let's give some examples of these. An example of a homogeneous mixture would be like Koolaid. We're going to talk about Koolaid a lot today. Heterogeneous mixtures would be like chicken noodle soup. Chicken noodle soup. Or concrete or marble. Remember that homogeneous mixtures also have another name, and the other name for homogeneous mixtures is solutions, which is the topic of this unit. So we are focusing mostly on homogeneous mixtures. Okay, so what does soluble mean? When we're talking about solutions, we're talking about things that are soluble in other things. So when we're speaking of something that's soluble, what we mean is soluble means dissolvable. That's one way of putting it. Dissolvable. I ask you guys how to spell things because you can't answer me. Dissolvable or capable of being dissolved, obviously, means the same thing. Capable of being dissolved. So this is just basic terminology here on things with solutions. So if one substance is soluble in another substance, it means that it dissolves in that other substance. So we'll use that quite regularly to talk about things. Okay. So again, remember, when it comes to mixtures, solutions is another fancy word for a homogeneous mixture. Mixture. Oh, I did not like that. Maybe I shouldn't turn that on. Solutions are homogeneous mixtures of 2 or more substances in a single phase. Of 2 or more substances in a single phase. And there are 2 parts to a solution. Again, you guys know this already, so this is just kind of basic review. The 2 parts are the solute and the solvent. And I hope you know, if I asked you to tell me what those are, the solute, of course, is the thing that gets dissolved. And the solvent is the thing that does the dissolving. And again, we talked about this before, but the solute is usually, I say usually because it's not always, it's the one that is lesser in amount, and the solvent is greater in amount. Usually you have more solvent than solute. So if you're thinking about something like Kool-Aid, obviously you have much more water than you do Kool-Aid powder when you're making that. But it's not always true. All right, so let's kind of dive into solutions a little bit more. We can have different solute solvent states of matter combinations, and I want to talk about them in some examples. So what I mean by that is, let's talk about our first example. If I had the solute, again, this is the thing that gets dissolved. If the state of matter of the solute is a gas and it's getting dissolved into a liquid, so think about that just for a minute. The solute, the thing that's getting dissolved, is a gas, and it's being dissolved into a liquid. So think about a common everyday example of something that you know that is a gas dissolved into a liquid, which of course we know is, like an example of this would be pop, soda, wherever you're from, whatever you want to call it, soda pop. So we have gas particles that are dissolved into liquid. Normal seawater, normal almost any kind of water has dissolved gases in it, but pop is a very obvious example. So another solute solvent combination would be, what if we took a gas and dissolved it into another gas? So the solute, the thing that's getting dissolved, is the state of matter gas, and it's being dissolved into a gas. Can you think of what would be an example of this? An example of this might be just simply the air that we're breathing. Think about you're breathing out carbon dioxide, right in front of your face. Carbon dioxide is coming out of your mouth, and it is mixing with the air that's around it. So it's being dissolved within all the other gases that are in the air. So gas in gas. Okay, so another example or another state of matter combination would be liquid solute. The thing that's getting dissolved is dissolving into a liquid. So an example of a liquid dissolved into a liquid, for example, would be alcohol in water. Alcohol. Sorry, my cat just jumped up beside me. Alcohol. And she's nuzzling up against me. Alcohol in water. Now, we know that this is a thing because rubbing alcohol that you can buy at the store is not always 100% alcohol. It is, you can get 90%. You can get 70% rubbing alcohol. You can get 65% rubbing alcohol. So basically what that is how much diluted down it is with water. So it's a liquid dissolved into a liquid. Okay, let's see, some of these other examples are not quite as common. So we'll talk about them. What if we were dissolving a liquid into a solid? Now, not a solid into a liquid like Koolaid, but a liquid dissolved into a solid. So we have tiny particles of liquid that are getting dissolved within a solid. And this is an odd one. I really only know one example of this. I mean, there's probably lots of examples, but an example of this is the dental fillings that are silver colored, which not a lot of us have anymore. We have the tooth colored ones. But basically what that is it is liquid mercury, which of course they don't do anymore, into solid silver. And that's what makes them that color. But of course we don't put mercury in our dental fillings anymore. And if you need to put what that is, dental fillings. They used to make it that way. They would take liquid mercury, of course, and dissolve it into silver. Okay, another example or another combination would be solid into liquid. This is a really easy one. You could probably think of a million examples of this. Give me an example of a solid dissolved into a liquid. Of course, we talked about Kool-Aid. Even just salt water is an example of a solid dissolved into a liquid. And then the last example, of course, is if we take a solid solute and dissolve it into a solid solvent, which of course if we take two solids and try to dissolve them in each other, that's not going to work. However, solids, if they're melted down, one can be dissolved into the other. And this is how things like steel are made. Do you know what things like it's definitely not how you spell steel. Steel. And any type of alloy, really. Alloys are made by dissolving a solid into a solid. Even like gold. A lot of our gold jewelry is not made of 100% gold. It's made of an alloy. Okay. Or even like steel, obviously, as an example, but brass, your brass instruments, they're made out of alloys, solid dissolved into solid. Actually, those pennies, the alchemist penny lab where you turn the penny gold, that was made of brass. So you made an alloy when you were putting your penny into the fire. Okay, so let's dive a little bit more into an expansion of solutions. So solutions, of course, are when one substance is dissolved into another, right? A homogeneous mixture where substances are combined and dissolved. But there are expansions on solutions. So there's solutions, there's colloids, and suspensions. So these other two words mean something as well, of course. They are something as well. So what are they? Let's discuss each one of these. Let's make little categories here. So we'll just draw arrows. That'll be easier. And they're kind of separated based on their particles. Okay, the particle size. So solutions have the smallest particle size of the three when we're talking about the solute. So solute particles that make up solutions are so tiny. They fall within the less than 1 nanometer, and this is important because the size of these particles is what dictates which one they are. So the size of the particles of solute are less than 1 nanometer in size. And because they're so tiny, you can't actually see them. So think about if you make Kool-Aid and you have a glass of Kool-Aid in front of you, you can't see the Kool-Aid powder anymore once you have dissolved it into the water because the particles are so tiny. Let me see. There's more I want to say about that. Okay, we'll come back. We'll jump back in once we identify some more things. So colloids are the in-between phase. So they're not the smallest and they're not the largest solute particles. They're the medium-sized ones. They're right in between the solute size particles of solutions and suspensions. And they have particles that are, I'll put a star to separate it, 1 nanometer to 1,000 nanometers in size. And colloids are unique because, and we'll talk about this on the next slide, they scatter light when you shine a light through them. Whereas with a solution, they do not scatter light. So think about just for a minute, if I took a glass of Kool-Aid or just a glass of salt water, because that's a really common thing, and I shined a light through it, the light would just go right through it. It would not scatter the light. You would not even see the beam going through it. It does nothing for it. However, colloids are unique, and once we discuss some examples of colloids, they will scatter light when you shine light through them. Suspensions are the largest of the particles. They are larger than 1,000 nanometers. Larger than 1,000 nanometers in size. So the solute particles are so big in suspensions that they're called suspensions for a reason. They need to be mixed up, and if you leave them set, they will eventually settle out. So we're going to jump down here and put a little star. They will settle out over time. So if you take Kool-Aid, let's go back over here to solutions to compare that. If you take Kool-Aid and you leave it set for like days, the particles never settle out. Never settle. You're never going to get the Kool-Aid powder to be at the bottom of the cup and all the clear water to be at the top. That just doesn't happen with solutions. And the same doesn't happen with colloids. They never settle out either. Never settle. But what happens with suspensions, and I'll give you an example of what a suspension is. An example of a suspension would be muddy water. So think about when you walk through a puddle and there's dirt at the bottom of the puddle, and you take a step into the puddle and you kick up all that dirt that's at the bottom, and all of a sudden the puddle looks cloudy and you can't see through it anymore because it's a muddy puddle. But if you leave the puddle sit undisturbed, all of that heavy dirt, because the particles are so large, will eventually settle to the bottom of the puddle, and you'll see clear water at the top again. And I mean, you see the same thing in a lake, and all the dirt will be at the bottom. That doesn't happen with colloids or solutions, but it does happen with suspensions because the particles are so large. In comparison to the do not scatter light and scatter light thing with suspensions, they are completely opaque, I believe is the word, not transparent. So they don't have any scattering of light and they don't let light through at all. So they are not transparent. So they're just going to block light whenever it's shown through a suspension. Transparent, not transparent. Okay, let's see what else we want to talk about here. Solutions, and we talked about this before. Solutions are homogeneous. Colloids are heterogeneous. And suspensions are heterogeneous. So there's a difference right there. You can see differences in colloids and suspensions. I would argue not as much in colloids, because once we go through some examples of colloids, you might think like, well, I can't really see the differences like I can suspensions, but you clearly can see differences in suspension. Okay. Let me see. It's ruffling my papers around here. All right. We just have a few minutes for the 20-minute. Okay, so I'm going to cut off this video now. I do want you to pick up and watch the next video in a minute. Do I want to do that? No, I think I might be okay. Okay, I think I'm going to keep going. I think we're all right. Just have to run in to help my poor child who's not feeling well, so I think we're just going to go on. Okay, so just like solutions, colloids have this weird and unique set of like solid into liquid, liquid into gas, gas into gas phases where we can discuss, but they also have different names for all of those things. So if we look back here, there's not a specific name for a solution in which a gas is dissolved into a liquid. We just have examples of it. But with colloids, there's this whole different classes of colloids that things fit into. And when we talk about colloids, again, they're like in this middle category. They're in the middle category of size of their solute particles. When I think, excuse me, when I think of colloids, I think of, I don't know, like an example of a colloid is shaving cream, and butter, and paint, and mayonnaise. Like all of these are examples of colloids. They're like, I don't know, blubbery things, for lack of a better word. A lot of them are. So we're going to go through the different classes of colloids, talk about the phases they are, and I'm going to give you an example of each one of them. Okay, so the first class is, again, we're talking about phases, so we're still talking about solute and solvent. A solid dissolved into a liquid. Solid dissolved into liquid. I wonder if I would be better off typing this. Let's do it. Okay. Might as well. Why not? Okay. Solid into liquid. Feels like I should have put this over here. Okay, so this class of colloid, sorry, it's the wrong spot, is called Sol, S-O-L. That's what the name of a solid colloid, solid solute dissolved into a liquid is for this particular colloid. And they just have all these weird, unique names that we're going to list. An example of this is, and just as I said before, this is paint. Let's think, and mud, and we'll talk about both. Think for just a minute what paint is. Paint is actually a liquid, okay? So think it's a liquid, it's water. That's what paint is, or other things, whatever else, whatever other solvents they use to as part of the paint. But basically, paint is solid pigment particles that are dissolved into liquid. And then you paint it on the wall or on your canvas, and the liquid evaporates, and the solid is left over to be stuck on whatever you wanted to paint. So think about when you go and buy a gallon of paint at the store. Um, what do you get? You have to give it to the people, and they have to shake it all up. They have to put it in the machine and shake it. And if they don't do that, there's a layer of liquid at the top because some of the solid has separated from that, because it is solid pigment that is dissolved into liquid. Mud is the same thing. Now, this is not like the muddy puddle we were talking about because that's a suspension, but actual like good mud. Did you ever play in mud when you were little? If you take mud and squish it in your hands, it's squishy. It is solid dirt that's dissolved into liquid water. That's what mud is. But the particles are big enough that they don't fit into the category of a solution. So that's the difference in these things. Okay. Next example, excuse me, is called gel. Hop over here and hope this works. Gel is solid network in a liquid. Solid, which is a little different than just a solid. Solid network into a liquid. So we're taking a solid network, a covalent network compound, and dissolving into a liquid. An example of this is gelatin. Now, we're not talking about jello, not like Jello, jello. We're talking about gelatin. And gelatin, if you know, is solid cow bones that are dissolved into liquid water. That's what gelatin is. And again, think about what gelatin forms, that blubbery type of feel to it. That's characteristic of colloids. So solid cow bones dissolved into, or animal bones dissolved into liquid, creates the colloid gelatin. Okay, next example is liquid emulsion. Liquid emulsion, this is a liquid into a liquid. This is a unique one. Liquid into liquid. A couple examples of this. So, how many of you drink 2% milk? How many of you drink 1% milk, or skim milk, or whole milk? So, what milk is that you buy at the store, and those percentages are basically how much watered down, how much straight out of the cow, which is whole milk, basically, and how watered down, which would be skim milk, your milk is. And it is a liquid dissolved into a liquid. And they are larger particles, because what happens over time, if your milk sits without you touching it, you get little layers. You can see the water layer at the top. So basically, the percentage that the carton says of the milk that you drink is how much liquid cow, straight out of the cows, dissolved into water, or vice versa, depending on how much you have in there. Another example is mayonnaise. So if we have any chefs in the room, mayonnaise is egg yolk, and, which is liquid, of course, and oil. So like a vegetable oil, and the two things are emulsified together, if you've ever heard that word, dissolved into each other to form a colloid, mayonnaise. So these are all, like I said, these are all examples of one phase dissolved into another phase to create a type of solution, but it's a colloid because it has larger particles. Okay, the next one is foam. This is gas into a liquid. This is a fun one. Gas into liquid. Example of gas dissolved into a liquid. So think about that. Gas dissolved into a liquid before, when we were talking about solutions, was pop, soda pop. Gas dissolved into a liquid in this particular example, when it comes to colloids, an example of this is whipped cream. Whipped cream, right? Because in the whipped cream container, you can hear the liquid in there, right? That's the liquid, that's the solvent it's getting dissolved into. And then when you push the little button, you're pumping gas into it. Gas particles are going into the liquid. in making whipped cream. Also, shaving cream is an example of this for the same reason. Shaving cream, even the shaving cream that you put into your hand and it's a gel, and then you rub your hands together and it foams up, you are adding gas into that liquid and creating a foam, colloid. Next one is solid aerosol. Solid aerosol. Okay, this one is solid into gas. So this is different, okay? Solid into a gas. So think what that means for a second. Think about an example of something where we have solid particles that are dissolved into a gas. Solid particles dissolved into a gas. And the best example I can give you of this is smoke. When somebody is smoking, or even like fire, if you go to a campfire and smoke from the campfire, that is solid particles. Smoke is solid particles, like if a cigarette smoke is solid particles. That's why it's so bad for you, because it sticks in your lungs, that tar. But it is solid particles that are dissolved into a gas, dissolved into the air. And you can see them oftentimes. Obviously, you can see smoke. And it will settle on things, right? When you leave a campfire, you smell like a campfire. It settles on your hair, it settles on your clothing, because it's those tiny little solid particles that are dissolved into the air, the gas that's around you, and eventually they settle out on your clothes and your hair. All right, next one is liquid aerosol. Same idea, different thing. Liquid aerosol. All right, this is liquid into a gas. So think about a liquid being dissolved into a gas. Liquid particles, tiny little liquid particles that are floating around in a gas. What's an example of that? An example of that is clouds, basically. Fog or mist, clouds. Clouds and fog are basically just little tiny particles of liquid water that are dissolved into the air. So that's liquid aerosol. That's an example. And the last one is solid emulsion. All right, this is solid into, no, excuse me, liquid into a solid. Liquid into solid. So again, let's think about this for a second. Liquid that is dissolved into a solid. And an example of this is cheese. Do you ever hear the nursery rhymes about, I don't even know what nursery rhyme it is now, but the nursery rhyme about curds and whey. The curds and the whey, one of them is the liquid, one of them is the solid. And that is a solid emulsion, colloid. Cheese is, because when you squeeze cheese enough, it gets all the whey, the liquid, out of it, and you're left with the solid cheese. Okay, so those are all the different examples of colloids. Lots of things that we use in our everyday life are examples of colloids. All right, so when we were talking about how colloids scatter light, there's this idea called the Tyndall effect. So we're defining it here first. Light scattered by colloid particles in a transparent medium. The Tyndall effect is when light scatters, light is scattered by colloid particles in a transparent medium. Right, so the best example I could give you of the Tyndall effect is, why do we have fog lights? First of all, where are the fog lights located on your vehicle? Down below, right? They're down below your normal lights. Your headlights come out the front, fog lights set lower than that. And they set lower for what reason? So say you're driving at night and you hit an area where it's foggy and it's hard to see, even though you have your lights on. Do you turn your brights on so you can see better? Of course you don't. If you turned your brights on, what happens? The bright light reflects off of the fog and, blinds you even more. So fog lights set lower so that the reflection back up um, is not in your eyes as the driver. It shines out to light the way for you, but doesn't reflect back. So basically, lights and fog lights. So we set up here fog and clouds as an example of a colloid. When you shine light into a colloid like fog, it scatters those particles, and it will scatter them and reflect them right back up into your eyes. And that's, again, why we have fog lights placed where we have them. I'm going to put fog lights, and hopefully you can remember what we just talked about. Fog lights. Let's put headlight is reflected off of the fog and into the driver's eyes. So fog lights set lower so they don't reflect up into your eyes. Okay. Well, I didn't mean to put that twice. We're not going to talk about Brownian motion. I don't believe that's anywhere later. But basically, Brownian motion is just colloid particles vibrate. They just vibrate in place because there are little electrical impulses that are going on within a colloid, and they just are, if you could look at them under a microscope. Brownian motion is just that vibrating motion the colloid particles do. So you can jot that down if you want. Yes. Okay. So let's talk about electrolytes and non-electrolytes, what they are. These are common words for us. Any substance that dissolves in water does one of two things. It either yields molecules or it yields ions. Yields molecules, and we'll give examples of these, or it yields ions. Okay, so when you take a substance, now we're going to jump back to solutions. Okay, it's important that I put this. I may have lost my pen. There it is. Okay. So important that I put this is regarding solutions, because we jumped into, of course, suspensions and colloids for a bit. When we have a liquid, mainly water in this particular circumstance, and we take a solid and we dissolve it into water, it will do one of two things. So let's think just for a second about sugar. If I have a cup of water here and I take sugar particles, I take a spoonful of sugar and I drop it into this water. What I'll end up with is tiny little sugar particles. Sugar, sugar, sugar. It's always going to stay C6H12O6. It's never going to break apart into anything smaller than that. So we just have tiny little individual molecules that it dissolves into when we put it in water. However, if I take, so this would be covalent compounds like sugar. If I take an ionic compound and I put it in water, like table salt, say I took a spoonful of table salt and put it in here, it does not stay as NaCl, NaCl, NaCl. It doesn't stay as salt, salt, salt. It breaks up into Na plus and Cl minus. It breaks up into all the little ions that make it up, and they stay separated until the water goes away. So ionic compounds like salt, NaCl, will yield ions in solution versus covalent compounds, which will stay as whole molecules. And there's the two differences. Now, what that means to us is that dictates whether the substance is an electrolyte or a non-electrolyte. So things that break up into positive and negatives, like the NaCl here, this fits under the category of electrolytes. And an electrolyte is something that, when dissolved in water, it conducts electricity. A solution that conducts electricity. And then, of course, a non-electrolyte is a solution that does not conduct electricity. So let's talk just for a second why it does this. So my engineers in the room, Obviously, water conducts electricity, period. So let's forget about the fact that we have water both involved in these things. But what does electricity need in order to flow? Well, electricity flows through charges. Okay, so of these two things, this sugar that I just drew and this NaCl that I just drew, obviously the NaCl has all of these positive and negative charges, and positive and negative charges are what helps to carry a current. So electricity is going to flow through substances that break apart into ions. So a substance that yields ions creates an electrolyte. Substances that yield molecules create non-electrolytes. Now, where have we heard the word electrolyte before? All the athletes in the room would say, my Gatorade or my Powerade or my sports drink. Electrolytes are things that you drink that when you drink them, they break apart into ions. So in your body, you have these little positive and negative charges floating around, these little ions. And what do? They help your body carry electrical impulses. They help your muscles work better because your muscles work with electrical impulses. So without all these little ions floating around in your body from your Gatorade electrolyte that you drink, you don't have as efficient electrical impulses because your body's not being able to conduct electricity as well. So that's essentially works the same as what we were just talking about here. Just simply now, of course, they put sugar in your Powerade and your Gatorade too, but that's just for flavor. Because who wants to just drink salt water when they're trying to work out? Okay, let me see what I have on time. All right, just a couple more minutes. Okay, so we're going to jump to here the next couple of minutes. So, and if if you only have a single period today, you can just finish watching the notes later because we won't cover this again in class. It shouldn't be more than just a couple minutes. If you are a double period, you need to finish through these because you need to know how to read solubility curves in order to do the worksheet that's for next period. Okay, there are 3 factors if I want to make something dissolve in something else. Okay, the solution process. So I'm trying to get something to dissolve in something else, and we're specifically going to talk about Kool-Aid because, who doesn't make Kool-Aid? When we're making Kool-Aid, there are 3 things, and this is true of anything that you're trying to get to dissolve in anything else, 3 things that we can do that help to increase the rate that something dissolves. So when you're making Kool-Aid, the first thing that you do is you dump the Kool-Aid powder into the water and you just leave it sit and it magically makes Kool-Aid, right? No, you have to obviously stir it. So the first factor that helps something to dissolve in something else is you agitate the mixture. Basically stir it up. That will help the solute dissolve quicker in the solvent. Another thing that you can do is you can increase the surface area of the solute. Have you ever been to a restaurant and we have those little packets of sugar? I don't even know if they do it anymore. They probably don't even leave those on the tables anymore, but they used to a long time ago. Maybe you remember there were little blue packets and pink packets and yellow packets, like the Sweet and Low and the artificial sweeteners. Well, most of those artificial sweeteners were like a really fine powder, like a powdered sugar almost, and they would dissolve right away versus like there was the little brown packets of sugar in the raw, which had gigantic crystals and you had to stir and stir and stir forever. Well, that's because when you crush something up, you increase the surface area, and therefore there's more surface area for the solvent to be working on and dissolving it. So if you wanted Kool-Aid, if you wanted to make Kool-Aid faster, you could crush up all the powder into a finer powder and it was actually dissolve. So basically we do this by crushing up solute. And the last thing that you can do in order to get something to dissolve faster is increase the temperature. And this is most of the time of the solvent. So if you make Kool-Aid with warm water, you'll get more sugar to dissolve into it than if you make it with cold water. And then you can slowly cool it down or put it on ice and it will actually be sweeter because you can get more sugar to dissolve in warmer water. Every solvent has a set amount of solute that can dissolve in it. So basically, There's a reason why they put on the Kool-Aid packet, add 2 cups of sugar. That doesn't mean you're supposed to add 4 cups of sugar, because what's going to happen with all of that sugar that you added that was beyond the amount that they said on the packaging? Well, it's all just going to settle out at the bottom. So every substance that gets dissolved in something else has a set amount of solute that can dissolve in it. Like that's a done deal. Kool-Aid just the same. Solubility depends on 3 things. It depends on the nature of the solute. And what I mean is it polar or nonpolar? It depends on the nature of the solvent. Again, we mean polar or nonpolar, because that dictates whether they will dissolve in each other. Polar things dissolve polar things, and nonpolar things dissolve nonpolar things. Remember when I put the styrofoam cup in the acetone the one day in class and it dissolved it? That's because they had the same polarity. And then temperature. We're going to learn how to read some solubility curves with temperature. Solubility is an equilibrium between dissolving and recrystallizing. Dissolving and recrystallizing. Okay, so basically when we have a solution, so even when we make Kool-Aid, we dissolve the Kool-Aid powder. And as we're dissolving it, particles are breaking apart. They're dissolving, right? But then also what's happening is they're coming back together and forming crystals again. And once they get to a happy medium where the rate at which the Kool-Aid particles are dissolving and the rate at which they are recrystallizing back together is equal to each other, then we have a saturated solution. We have the maximum amount of solute, the set amount of solute that water can hold, the maximum amount of Kool-Aid powder that you can put into a pitcher of X amount of water. So we're going to kind of define this. So solution equilibrium is, this is basically that physical state in which the opposing processes, of dissolution and crystallization of a solute occur at equal rates. That happy place where particles are dissolving and they're recrystallizing at the same rate, and therefore it has reached solution equilibrium. And it has created what is called a saturated solution. A saturated solution is when the solvent is holding the maximum amount of solute. Solvent is holding the max amount of solute that it possibly can. One more crystal of solute is going to make it push it over the edge, or it's going to settle out at the bottom. So I guess we're going to put that. One more crystal of solute will settle out. So this is that point where you've put as much Kool-Aid powder as you possibly can in the amount of water that you're making Kool-Aid for. And if you put one more scoop or one more crystal even, it'll just float to the bottom and it will not be able to dissolve, no matter how much you stir it. Unsaturated would be if you didn't add enough. Solvent is holding less than the maximum amount of solute that it can. So it can basically hold more. And then supersaturated is a unique place. Supersaturated is when the solvent is holding more than it's supposed to. Solvent is holding more solute than it should at a given temperature. And the reason why it's doing this is because it had to be heated up you have to heat up the solvent, you have to dissolve more solute than you can, and then you have to cool it back down to its normal temperature. So it's at a point where it's just holding on to more. If you've ever made rock candy, that's how you do it. You take and heat up water and you dissolve a whole bunch of sugar in it, and then you slowly cool it down so that the water is holding more sugar than it's supposed to. So this is achieved. Spell this wrong. By heating. So here's a picture example. Obviously unsaturated, you don't have anything settling out at the bottom. Saturated, it means it's holding as much as it can. If you put any more in, it will settle at the bottom. And super saturated basically starts to form crystal towers, just like rock candy does. All right. This is a solubility curve, and you're going to work with these on a worksheet if you have a double period today. If not, you're going to work on it tomorrow. All right, so solubility. Let's talk about what solubility is. Let me get to the definition of this. Solubility is the amount. Let's define it here. The amount of substance required to form a saturated solution with a specific amount of solvent at a specific temperature. So basically, I mean, what this means is I could look at this graph and I could find out, all right, so say I wanted to figure out KNO3, potassium nitrate, and I wanted to know how much KNO3 could I dissolve in 100 grams of water? So you have to look at your y-axis here. Into 100 grams of water, how much of this could I dissolve if my water was 40 degrees Celsius? So I just follow this curve up, right? It's right about here. I'd go over and I'd say, oh, about 62 grams of KNO3 can dissolve in 100 grams of water. So it's just reading graphs, basically. Solubility curves are these. Now, this solubility curve shows us that almost all substances, as temperature increases, the solubility increases. Some by a whole bunch, some by not so much. There are a couple of substances, though, this specifically being one of them, Ce2SO43. This specifically one of them that decreases solubility as temperature increases. So we can look at this chart and interpret a lot of things from this. So basically what you are going to do now, and I hope I gave you enough information to do this, I think I did, is you're going to work through a worksheet. Again, this is if you have a double period today on Thursday. You're going to get the worksheet from the sub, and you're going to go ahead and work through. There's some definition stuff at the beginning of the worksheet. And then you're going to work through reading solubility curves. You're going to use the solubility curve that is given to you on the front side of the page, and you're going to answer all of the questions and then turn it in at the end of the period. It's something you can work on with your lab partner you're sitting next to. I mean, this is no different, really, I don't think, than I guess I could pull this up and do one with you just to make sure you know what you're doing. If you want to go ahead and figure it out, you can. If you want to stop here and just jump into it, if you feel like you don't know what you're doing, I'm going to go ahead and pull it up and see if I can go through a couple of them just so you guys know what you're doing. If you feel like you want to jump right into it and then you're lost, okay, this is all definition stuff. You don't need to do that. This worksheet, again, is a worksheet the sub has. So basically, you're going to take this solubility curve, and we'll just jump to one, okay? This solubility curves, these lines, dictate where a perfectly saturated solution is. So when it's asking a question about what amount will form saturated or unsaturated. So I'll jump and do number 18. So what amount of KClO3 will form a saturated solution at 80 degrees Celsius? So I'm going to find my KClO3 line, which is right here. I'm going to go to 80 degrees Celsius, right? And then I'm going to go over about 45 grams of solute. So the answer to number 18 would be 45 grams of KClO3 would form a saturated solution. There are some questions then later on using this same graph, same curves, that will ask you in 100 grams of water at 70 degrees Celsius, how much KNO3 will dissolve, make a saturated solution. But then it jumps down here and says in 50 grams of water. So you're going to have to look at how much NaNO3 will form in 100 grams of water, because that's what that's what our graph tells us. And then you're going to have to set up a proportion to figure out how much would dissolve in 50 grams. You guys are smart. I know you can do this. This last little section asks you to identify saturated, supersaturated, or unsaturated. So again, remember these curves. Exactly on this curved line is a saturated solution. Anything that would fall above the line would be supersaturated. Anything that would fall below the line would be unsaturated. So for the last one, you're looking up using these values and then identifying where they fall within that line. All right, that should be it. If you have 2 periods today, make sure that you're finishing this worksheet and turning it in.